In section 7.4, we're talking about operations with radical expressions. We're going to start off with square root expressions and then cube root expressions, and then practice simplifying. In this section, we're really going to talk about doing addition and subtraction. We talked a little bit about multiplication and division in the last class. So adding and subtracting radical expressions. First thing, we're going to start off with the easiest ones. Adding and subtracting what we call like radicals. Like radicals are radical expressions that have the same index and the same radicand. Okay, not that bad. The index is the same, so that means the cube root or the square root or the fourth root, that's the same. And the radicand is the same. We're taking the square root of 2, square root of 5, the cube root of 8, the cube root of 8. So they're the same there. If that happens, if we have a times the nth root of c plus b times the nth root of c, that is equal to a plus b times the nth root of c. A quick example of what that means. If I have something like 4 times the cubed root of 5 plus 2 times the cubed root of 5, that's 4 cubed roots of 5 plus 2 cubed roots of 5. 4 plus 2 is 6 cubed root of 5. And of course, it will work out the same way if we were subtracting. If we did 4 cubed root of 5 minus 2 cubed root of 5, that would be 2 cubed root of 5. You subtract the coefficients out. It's kind of like if you had 4x plus 2x, that would be 6x. Works the same way with like radicals. All right, we're going to jump to the practice problems for this. For problem 1, or practice problem 1, part A, we have 3 square root of 5 plus 4 square root of 5. 3 plus 4 is 7, so this gives us 7 square root 5. That's it for these. Nice, easy start. 2 cubed root of 7 minus another cubed root of 7 would just leave us with 1 cubed root of 7. All right, part C, 6 times 4 cubed, or 6 times the fourth root of m minus 3 times the fifth root of m. Are these like radicals? They are not. The indices are different. So this one is a fourth root. This one is a fifth root. That means that they're not like, so we can't simplify them anymore. Not like radicals. Nothing we can do there. Same for part D. In part D, we have the 4 square root of m plus 4 square root of n. This time, the radicands are different. One has an m, one has an n. Not like radicals, we can't do anything. And same thing for part E. 5 plus the square root of x, those are not like terms even. So we cannot combine them at all. It's as simplified as possible. All right. We can add and subtract many radicals by simplifying them and rewriting them as like radicals. Recall that we simplify radicals by removing the perfect nth power factors from the radicand. Once each radical is simplified, we combine the like terms. So what this is saying is, for some problems, they start off not looking like they're like radicals, but if we simplify each radical, they turn out to be like radicals, and then we can combine those like terms. Okay, I'm going to skip example 2 and go straight to the practice problems. For problem A, the square root of 54 plus the square root of 24. We see that they're both square roots there, but just looking at these problems, are 54 and 24 the same number? No, it doesn't look like these are like radicals at all. It doesn't look like we can really simplify this anymore, but we can. So let's just focus on simplifying the 54, or square root of 54 and the square root of 24. You want to think about what's the largest perfect square, since this is a square root problem, that you can pull out of 54 and 24. Okay, what are perfect squares? Perfect squares are numbers like 1, 4, 9, 16, 25. The numbers that you get when you square any of our, what do you call them? Geez, I can't think of them. When you square any of the whole numbers. For 54, 54 would be 9 times 6, is that the largest one? Yeah. So that's the square root of 9 times 6. 24 is 4 times 6. Okay. So the square root of 9, we know that's 3. So the square root of 54 becomes 3 square root of 6. The square root of 4 is 2. So this is 2 square root of 6. And then now we see that we have like radicals there. 3 plus 2 is 5. So this gives us 5 square root 6. Not really necessary. All right, on to B. We have the square root of 63 plus the square root of 700. Okay. Well, 63 is 9 times 7. And 9 is a perfect square. 700 is 100 times 7. You need that line. So this gives us 3 square root of 7 plus 10 square root of 7. 3 plus 10 is 13, so 13 square root of 7. All right, for A and B, we had square roots, so we were looking for perfect squares to pull out. For C and D, we have cubed roots, so we have to look for perfect cubes to pull out. All right, for part C, is there any perfect cube that's a factor of 30? Our perfect cubes are like 2 cubed, which is 8. 3 cubed is 27. 4 cubed is 64. None of those are factors of 30, so we can't really simplify that much more in terms of cubed roots. And then if we can't simplify that one, 192 definitely won't factor to a 30. That one can't be simplified anymore. Okay, and then the next one, we have cube root of 16. Okay, now we're working with something here. 16 has a couple of, well, not a couple. It has one perfect cube in it, 8. 16 is 2 times 8. And then 250. That's 2 times 125, and 125 is 5 cubed. All right, so let's write this out. We have 6 times the cubed root of 8 times 2 minus 2 times the cubed root of 125 times 2. The 6 stays on the outside. The cubed root of 8 is 2. So that's 6 times 2, square root of 2, minus 2 times the cube, I'm sorry, that should be a cubed root. The cubed root of 125 is 5, and then cubed root of 2. All right, 6 times 2 is 12. We get 12 cubed root of 2 minus 10 times 5, or 2 times 5 is 10 cubed root of 2. And finally, 10 minus 12 leaves us with a 2 cubed root 2. All right, so using some of the techniques we learned in the last class, with simplifying radical expressions, if we have 2 radicals that are being added or subtracted, they may simplify to be like radicals, and then we can combine them. All right, so we're going to do, for the next 3 examples, various different problems with adding and subtracting radical expressions. Again, I'm just going to jump past that and go straight to the practice. So we're going to simplify and assume that all of the variables represent positive numbers here. In order to simplify these radical expressions, again, we want to try to simplify each term so that what's left under the radical is the same for each expression. And then from there, we can combine, add or subtract the like terms. I'm going to have to rewrite these down here. So for part A, we have negative square root of x plus a square root of 9x, I'm sorry, plus square root of 25x. So here, where do we start? We have a 9 under the square root and a 25 under the square root. We know the square root of those numbers, so we can factor that out. This would be negative 3 times 3 square root of x plus the square root of 25 is 5. So we get 5 square root of x. And then ta-da! Both of those terms are square root x terms. Negative 3 times 3 is negative 9 root x, then plus 5 root x. And from here, we just add the coefficients. -9 plus 5 is 4, or -4. -4 square root of x. And that's our final answer for A. For part B, we have the square root of 54x squared y squared minus 3 square root of 24x squared y squared. All square roots here. All right. 54, again, when 54 is not a perfect square, but we want to try to factor out the largest perfect square that we can find in 54, and that would be 9. So this would be 9 times 6, yeah, times x squared times y squared minus 3 square root of 4 times 6 x squared y squared. Now we can factor a lot, or not factor, pull out lots of things from under the radical. The square root of 9 is 3. The square root of x squared is x. The square root of y squared is y. So we get 3xy, square root of 6. Then minus 3 times the square root of 4 is 2. The square root of x squared is x. The square root of y squared is y. So 2xy, square root of 6. All right, we have 2 radical 6 expressions here. These are like expressions we can simplify. First, let's rewrite this as 3xy root 6 minus 6xy root 6. Then 3xy minus 6xy would leave us with a negative 3xy root 6. All right. As you can see, hopefully already, these problems kind of start building on each other. The skills that we're learning in that we learned in exercise 2, we're going to use that and add on to it, make those a little more challenging in exercise 3. Oh, I'm going to run out of space, but that's okay. Part C. We have the square root of 75 x squared y squared minus 2 square root of 75 x squared y squared. Well, there's a couple of ways that we can do this one. First, they're already written as like radicals. Both of them are square roots of 75 x squared y squared. So we can subtract. We have 1 minus 2 of those. That leaves us with negative square root of 75 x squared y squared. It's like if you have x minus 2x, that's negative x. Here we get negative this whole radical. All right, now we can actually simplify the radical. We're taking square roots. 75 is 25 times 3. Then we have times an x squared and a y squared. Our negative still out front. The square root of 25 is 5. The square root of x squared is x. The square root of y squared is y. And we still have our radical 3 left over. So negative 5 xy square root of 3. Last one, it'll fit down here somewhere. Part D, the square root of 44 x to the 5th y to the 8th plus 2 square root of 99 x to the 5th y to the 8th. Okay, first thing, we have square roots, and then the numerical factors are 44 and 99. We can write that as 4 times 11 and 9 times 11. All right, so 4 times 11, x to the 5th, y to the 8th, plus 2 times the square root of 9 times 11, x to the 5th, y to the 8th. All right, what things can we take out? We know the square root of 4 is 2. The square root of x to the 5th, we can pull out, that's x squared times x or x to the 4th times x. Actually, that might be a better way to write it so that you can visualize this. X to the 5th is x to the 4th times x, and y to the 8th, that's fine, we can leave it as y to the 8th. And then plus 2 square root of 9 times 11, x to the 4th times x times y to the 8th. The reason that I left the y to the 8th as a y to the 8th is if our exponent is even and we have a square root, we can just divide by 2 to simplify. So that's what we're going to do here. All right. Square root of 4 is 2. The square root of x to the 4th would be x squared. So we can pull out an x squared. And the square root of y to the 8th would be y to the 4th. So we have 2x squared y to the 4th, and we still have a square root of x left under there. Oh, square root of 11x. Okay, plus 2 times the square root of 9 is 3. The square root of x to the 4th is x squared. The square root of y to the 8th is y to the 4th. And then we're left with square root of 11 times x. All right, last step here. 2x squared y to the 4th root 11x plus 6x squared y to the 4th root 11x. If we add the coefficients, 2 plus 6 gives us 8x squared y to the 4th root 11x. So far, we've been doing problems with adding or subtracting like radical expressions, or if they aren't like, we simplify them. And then if we end up with like radical expressions, we can combine them. Next, we're going to look at multiplying radical expressions and using the distributive property. Let's jump to our practice ones. All right. So for all four of the, for the first problem, I should say, that we see here, notice there's a radical on the outside of the parentheses and then 2 radicals being added on the inside. This is a setup where we're able to use the distributive property to solve. If you look at part B, we have 1 plus the square root of 3 times 2 minus the square root of 3. So 2 terms are 2 binomials. We learned how to multiply terms like that by using the FOILing method. Okay, part C, 3 plus the square root of 5 all squared. Again, we can use FOILing for that as well. And for part D, we can FOIL. And we can use, or you'll notice that some of the techniques that we saw when we were multiplying rational expressions back in chapter 5, the rules that we learned there kind of still work. Well, not kind of, they do still work here for radical expressions. All right, first thing, we multiply the square root of 7 times the square root of 5 plus the square root of 7 times 2 square root of 7. This gives us the square root of 35 plus 2 square root of 7 times square root of 7 would be the square root of 49. Or another way you can do this is if you multiply something by its, or a radical by itself, the radicals cancel out, you just get the number that's underneath, which we'll see here. That's 35, or square root of 35 plus 2 times the square root of 49 is 7. So we get the square root of 35 plus 14. Normally, when we write our answers that include a radical and a whole number, we write the whole number first and then the radical second. So 14 plus the square root of 35. All right, for part B, we have to FOIL. We're going to take this 1 and multiply by the 2 and the root 3. That gives us 2 minus root 3, and then root 3 times 2 and root 3 times negative root 3. So plus 2 root 3 minus root 3 times root 3, which is the square root of 9. So this becomes 2 negative, it's minus root 3 plus 2 root 3 leaves us with plus 1 root 3. And then minus the square root of 9 is 3. All right, now we can combine the constants. 2 minus 3 is negative 1, and we're left with negative 1 plus 3 as our answer. On to part C. Part C will work out very similar to part B. If you remember that 3 plus, I can't talk today, 3 plus the square root of 5 all squared. We cannot just square each term in the base there, but we can expand this and then FOIL. So we'll get 3 squared, which is 9, plus 3 square root of 5, plus another 3 square root of 5 plus the square root of 5 squared, which is just 5. Okay, one quick thing I want to point out. Notice here, when we multiplied square root of 7 times square root of 7, we got the square root of 49, which is just 7. When we multiplied here, the square root of 3 times the square root of 3, we get the square root of 9, which is just 3. You can go straight to just the 3 if you want. That's what I did here. When we multiplied the square root of 5 times the square root of 5, that's just 5. Okay, let's carry on with our simplifying. So we can combine the constants. 9 plus 5 is 14. And we can combine the radicals. 3 root 5 plus 3 root 5 is 6 root 5. Last one. Now notice how this is not similar. It's exactly the same as a minus b times a plus b, which we should know simplifies to a squared minus b squared. I'm going to FOIL this out and you'll see that yes, it does simplify to 7 squared minus the square root of 10 squared, which is 10. So 7 squared minus 10, our answer should be 39. Let's check it out. We have 7 times 7, which is 49, and then minus 7 root 10 plus 7 root 10. So those middle terms cancel out. And then minus the square root of 10 squared, which is 10. So those middle terms cancel out, and then we get 49 minus 10, which is 39. All right, let's keep rolling. The next section is very important, rationalizing the denominator of a radical expression. Usually when we have radical expressions that have a denominator, we don't want the radical in the denominator. Okay, so fractions that have radicals in the denominator can be difficult to manipulate. Rationalizing the denominator is a technique by which a fraction with a radical in the denominator is converted to an equivalent fraction whose denominator is an integer. You have to get rid of the radical in the denominator. To rationalize something like 1 over root 3, we're just going to multiply by root 3 over root 3. And this technique is called, again, rationalizing. It's changing your or rewriting your radical expression so that there is no radical in the denominator. Okay, when we do this, 1 over root 3 times root 3 over root 3 gives us root 3 over 3. So this term is exactly the same as this, but what we see there on the right is the rationalized form. All right, I'm going to skip past all of these examples and go straight to the practice with rationalizing. And again, anytime we have radical expressions that have a radical in a denominator, you will need to rationalize your denominator. For part A, which is 3 over the square root of 2, we have a square root of 2 in our denominator. So to rationalize this, we're going to multiply by, maybe I'll use another color. Multiply by root 2 over root 2. Then that gives us 3 square root of 2 over the square root of 2 times the square root of 2 is just 2. And that's it. For part B, 6 over 3 root 2. Again, we have to get rid of that root 2 in the denominator, so we're going to multiply by root 2 over root 2. Remember, you have to multiply the numerator and denominator by the exact same thing, otherwise you're changing the problem. Multiplying by root 2 over root 2 is just like multiplying by 1, so technically we get something equivalent to our original expression. All right, in the numerator, 6 times the square root of 2 can't be simplified anymore. And then in the denominator, we'll get 3 times the square root of 2 times the square root of 2, which is 2. So 6 root 2 over 6, that just simplifies to the square root of 2. All right, in part C, 3 over radical xy. To rationalize this, we're going to multiply by the square root of xy in the numerator and denominator. That gives us 3 root xy divided by xy. And that's it, can't be simplified anymore. All right. Next one, 2 over the square root of 3x. We'll have to multiply by the square root of 3x over the square root of 3x, which gives us 2 square root of 3x over 3x. And nothing simplifies there. Now for part E, sorry, this very crooked line is bothering me. For part E, we have radical 5 over 7. And you might be thinking, well, that doesn't look like just a radical in the denominator. The whole thing is a radical, which is true. But if we break this down a little bit, this is the square root of 5 over the square root of 7. We can take the square root of the numerator and denominator. Then from here, we see that our denominator needs to be rationalized. So we'll multiply by root 7 over root 7. This gives us, so we have the square root of 5 times the square root of 7. We can combine those to the square root of 35. And then over root 7 times root 7, which is just 7. So root 35 over 7 is our final answer. And we can do part F similarly to what we just did in part E. The square root of 2y over 3 is the square root of 2y over the square root of 3. Then we need to rationalize that denominator by multiplying by the square root of 3 over the square root of 3. And then that gives us, in the numerator, the square root of 2y times 3 would be the square root of 6y over 3. All right. So again, this is rationalizing our denominator when we have just one nice radical in our denominator. So if you have one radical term in your denominator to rationalize, you multiply by that exact radical term in the numerator and denominator, and then simplify. Now, of course, all of our problems are not going to be this nice. There are going to be times where your denominator has a radical being added or subtracted to something else, either another radical or a constant. In cases like that, the technique that we use is to multiply by the conjugate, okay? Remember, the conjugate of a binomial, we have it written here. If we have A plus B, the conjugate is A minus B. We want to change the sign between the two terms. A plus B and A minus B are conjugates, and when we multiply conjugates, we end up with A squared plus or minus B squared, the difference of squares. We're going to use this fact to help us simplify or to help us rationalize expressions that have binomials, including radicals in a denominator. The trick is, or the technique is, to multiply by the conjugate of the denominator. All right, what does that mean? So when we look at problem A, 3 over 1 plus the square root of 5, we have to get rid of the square root of 5 in our denominator, but just multiplying by the square root of 5 won't work because we have that 1 there, right? So the technique that we use here is to multiply by the conjugate of the denominator. The conjugate of 1 minus the square root of 5, I'm sorry, 1 plus the square root of 5 would be 1 minus the square root of 5. And we have to multiply the numerator and denominator by this. All right, so in our numerator, we have 3 times 1 minus the square root of 5, which would be 3. I'm just going to write it this way for right now. 3 times 1 minus root 5, and then divided by 1 plus root 5 times 1 minus root 5. I'm going to FOIL this all the way out just one time, but you'll notice that it's just going to simplify to 1 squared plus the square root of 5 squared. I'm sorry, 1 squared minus the square root of 5 squared. So this would be 1 minus root 5 plus root 5, and then minus root 5 times root 5 is 5. So we get 3 times 1 minus root 5 over 1 minus 5, negative 4. And that's our answer. If you want, you can move the negative to the front. So negative 3 times 1 minus root 5 over 4. Or if you really want to distribute in the numerator, you can do that as well. So 3 minus 3 root 5 over 4. All right, for part B, root 5 over 1 plus root 2. The conjugate of the denominator is 1 minus the square root of 2. And if we multiply our numerator and denominator by this, we get the square root of 5 times 1 minus the square root of 2 over, again, we're using the fact that a minus b times a plus b equals a squared plus b squared. So we can save ourselves some time by, oops, not doing that, squaring the ones and squaring the square root of 2. That'll give us 1 squared minus root 2 squared. So we have the square root of 5 times 1 minus root 2 over 1 minus 2, which is -1. So that's the square root of 5 times 1 minus the square root of 2 over -1. And we can simplify the numerator a little bit. The numerator, if we distribute, would give us the square root of 5, and then minus the square root of 10. And then that's still divided by -1 or times -1. You can leave it like this, or if you want, you can write negative root 5 plus root 10. Either way, I would accept the answer. Part C, root 3 over root x plus root 7. All kinds of radicals going on here. We're just concerned though with what's going on in the denominator. We want to multiply by the conjugate of the denominator, which is the square root of x minus the square root of 7. Okay, and remember, we're multiplying these entire expressions by each other, so technically there should be parentheses there. Okay, in the numerator, we have root 3 times root x minus root 7. We can distribute and simplify that some more, which we will. And then in the denominator, we'll end up with the square root of x squared, which is x, minus the square root of 7 squared, which is 7, x minus 7. All right, simplifying what's going on in the numerator here. We distribute the root 3, that's the square root of 3x minus the square root of 21 over x minus 7. That's all we can do to simplify here. Last one, the square root of x minus the square root of 3 over the square root of x plus the square root of 3. Now the conjugate here is the term that we have in the numerator. So the conjugate of the denominator is root x minus root 3. So we're going to multiply the numerator by itself. When we FOIL this out, what will we get? The square root of x times the square root of x is x, and then minus the square root of 3x minus the square root of 3x plus 3 over the square root of x times the square root of x is x minus the square root of 3 times the square root of 3, which is 3. And if we simplify this, we get x minus 2 radical 3x plus 3 over x minus 3. All right, we did it. So that wraps up section 7.4, which is about simplifying radical expressions. Again, this idea of rationalizing the denominator, you'll see this pop up in a lot of other sections going forward. Next, let's jump to section 7.5, where we talk about radical functions. And then in 7.6, we'll solve radical equations. All right, the first radical function that we're going to look at is the square root function. You might be thinking, we've already talked about square roots a bunch of times. What's different now? Well, now we're using function notation. So you plug in a number for x, and the square root function kicks out the square root. Because of how we define the square root, for this function, we can't take the square root of a negative number. So the domain of this function is all positive, or all non-negative numbers, I should say, 0 and then positive numbers. We can't take the square root of a negative. The graph of the square root function is shown there in figure 1. And then, as I mentioned, if you try to take the square root of a negative number, as we see here in the table, Your calculator will just say error, error, error. That's because the square root of a negative number is, it's imaginary. It's not a real number. And we haven't talked about imaginary numbers yet. All right, I'm just going to jump down to the first section where we practice evaluating square roots. This is just like we evaluate any other function. We're going to, if we want to evaluate these functions at x equals 4 and x equals -1, replace the x's with 4 and -1. For part A, f of 4 would be the square root of 4 plus 5. That's the square root of 9, which is 3. That's it. For f of -1, that's the square root of -1 plus 5. The square root of -1 plus 5 is the square root of 4, and the square root of 4 is 2. That's all. So f of 4 is 3, and f of -1 is 2. For g, g of 4 would be -5 square root of 4 plus 3. That's -5 times 2 plus 3. -10 plus 3 is -7. And then for g of -1, we have -5 times the square root of -1 plus 3. And then hopefully you recognize that we have a problem here. We can't take the square root of -1. So this is not a real number. And finally, for part C, h of 4 is the square root of 4 plus 12 minus 3. That's the square root of 16 minus 3. The square root of 16 is 4, and 4 minus 3 is 1. Okay, and last one, h of -1 would be the square root of -1 plus 12. Doesn't simplify nicely, but that's okay. Minus 3. That's the square root of 11 minus 3. And the square root of 11 is not a whole number, so we can't simplify that anymore. We'll just leave it like this in radical form. All right, so we evaluate square root functions and cube root functions, which we're going to talk about next, the same way that we evaluate any function. Plug in the number that you're given for x and simplify. All right, determining the domain of a square root function. As I have just mentioned, we cannot take the square root of a negative number. So that means that whatever is under the radicand has to be greater than or equal to 0. That's how we find the domain of a square root function. Take the radicand, set it greater than or equal to 0, and solve for x. All right, so I didn't erase the answers here, but this one's done for us. But let's look at how we got these answers. For f of x equals the square root of 2x minus 3, our solution here says that the domain is -3 to infinity, including -3. What does that mean? That means that the only numbers we can plug into this function are -3 or something bigger than that. Anything else gives us something that's undefined for this function. How do we get this answer? You take your radicand, 2x minus 6, set it greater than or equal to 0, and solve. That's 2x is greater than or equal to 6, and x is greater than or equal to 3. And interval notation, that's 3 to infinity, and we put brackets around the 3 to include it in the solution. For part B, g of x is negative radical or square root of x plus 2. What's under the radical or the radicand? Just the x. So we know that x has to be greater than or equal to 0. That's 0 to infinity, 0 included. And then last one, under the radical, we have 4 minus x. So we would say 4 minus x has to be greater than or equal to 0. This gives us that 4 is greater than or equal to x. So that means x is less than 4. Our answer would be from -infinity to 4, including 4. So anytime you're asked to find the domain of a square root function, take the term under the square root, the radicand, and set it greater than or equal to 0 and solve. And you should be able to write your answer in interval notation. All right, that was the square root. We also have cubed root functions that we need to talk about quickly. This is our last exercise from this section. The cubed root function is just cubing a number. Unlike the square root function, the cubed root function is defined everywhere. So the domain is all real numbers. We can take the cube root of positive or negative numbers so we don't run into any issues. Oh, I do want to stop here. This is what the graph of the cubed root of x looks like. And again, it's defined for both negative and positive numbers. So for part 3, okay. So f of 2 would be the cubed root of 2 squared minus 4. That's the cubed root of 4 minus 4, which is the cubed root of 0. Cubed root of 0 is 0. Nothing else to do there. Then f of negative 2 is the cubed root of negative 2 squared. Notice I put the negative 2 in parentheses because the negative is being included in the square as well. That would be the cubed root of 4 minus 4. So same thing, which is the cubed root of 0, and that's 0. So both f of 2 and f of negative 2 are 0. For g of 2 is 2 times the cubed root of 5 minus 2 squared. That's 2 times the cubed root of 5 minus 4. The cubed root of 5 minus 4 is the cubed root of 1. And the cubed root of 1 is 1. So this gives you 2. Just 2. G of negative 2 will work out the exact same way. This would be 2 cubed root of 5 minus negative 2 squared. But negative 2 squared is also 4. So we just get 2 times the cubed root of 1, which is 2. All right. So now we've talked about how to simplify radical expressions, how to add, subtract, and multiply radical expressions. In the last class, we talked about dividing and simplifying rational expressions. We know what the cube root and square root functions look like and how to evaluate them. Last thing we need to talk about is how to solve equations that involve radicals. So 7.6, in the previous sections, we covered the simplification and evaluation of radical expressions and their importance in the definition of radical functions. In this section, we solve radical equations. And the big thing that we want to use to help us solve radical equations is, well, one of them is the power rule of equality. If we have two expressions that are equal to each other, then if we raise both of those expressions to the same power, we should get something that's still equal. Okay, how is this helpful for us? We also know that the opposite of a radical or a root is an exponent or a power, right? So to undo the square root, we're going to end up squaring. And if you do something to one side of the equation, you have to do it to the other. To undo a cubed root, you're going to end up cubing. To undo a fourth root, you raise both sides to the fourth power. So we're going to use those inverse relationships to help us solve equations that include radicals. How do we solve square root equations? I just gave you a hint. You square both sides. All right, so solving square root equations algebraically. First, you want to get the term that has a square root involved isolated or on one side of the equation by itself. Then we want to square both sides of the equation to get rid of the square root. We square, and then you're going to want to solve the resulting equation. And then, of course, as with any equation, when we solve, we can check our final answers. So let's jump to practice problems number 1 in this section. For problem 1, problem A, our radical is already isolated. It's on the one side of the equation by itself. But if you look at B, C, and D, the radical is not isolated. So we'll have to do some stuff for B, C, and D before we square. But for part A, we can go straight to squaring both sides. If the square root of 2x plus 3 equals 4, then the square root of 2x plus 3 squared equals 4 squared. So that would give us 2x plus 3 is equal to 16. Once you square both sides, the square and the radical cancel each other out. Then we get this nice expression that'll either be linear or sometimes it'll be quadratic, some type of equation that we know how to solve. All right, for here, This is linear. We'll subtract the 3. That's 2x equals 13, and then divide by 2. X equals 13 over 2. All right, for part B, the square root of 5x plus 1 minus 2 equals 0. We can add 2 to both sides to isolate the radical. So we'd have the square root of 5x plus 1 equals 2. Then from here, we want to square both sides. The square root of 5x plus 1 squared just leaves us with the 5x plus 1. That equals 2 squared, which is 4. And then again, we have this linear equation that we know how to solve. Subtracting 1 from both sides gives us 5x equals 3. And then dividing both sides by 5 gives us x equals 3/5. On to C. In C, we have 2 square root of 3x plus 2 plus 6. So we have a few things going on. First, the radical is being multiplied by a 2, and then there's also a 6 being added. We need to undo both of those things before we square both sides. If we subtract these 6 from both sides, we have 2 square root of 3x plus 2 equals 2. And then if we divide both sides by 2, we end up with the square root of 3x plus 2 equals 1. Once you get to this stage, then we square both sides. That gives us 3x plus 2 equals 1 squared, which is just 1. If we subtract 2 from both sides, 3x equals negative 1. And if we divide by 3, x equals negative 1/3. All right. And last one of these, part D, 2/3 times the square root of x plus 1 plus 3 equals 4. We need to first subtract 3 from both sides. So we'll have 2/3 times the square root of x plus 1 equals 4 minus 3 is 1. Then to get rid of the 2/3, we have to multiply by the reciprocal, which is 3/2 on both sides. So multiply by 3 over 2. That gives us our radical, square root of x plus 1 equals 3/2. All right. Now our radical is isolated. We want to square both sides. And we're squaring this entire fraction. So that gives us x plus 1 equals 9 over 4. That's 3 over 2 squared. And then if we subtract 1 from both sides, x would be equal to 9 over 4 minus 1. We do need to simplify these fractions. That's 9 over 4 minus 4 over 4, which finally gives us 5 over 4 for our answer. All right. So for solving square root equations, we need to, if you look at those steps that we looked at before, there were 4 of them. First, isolate the square root or the radical term, then square both sides of the equation. And then here, we ended up getting linear equations once we square both sides. We know how to solve linear equations. Sometimes after you take the square of both sides and the square root equation, you end up with a quadratic equation. We know how to solve those also though. So in the next example or practice problems, we'll see those types of examples. So still solving square root equations, but when we square both sides, you'll see we get different types of equations to solve. All right, for the first one, the square root of x plus 2 minus 2 equals x. We need to add 2 to both sides. So the square root of x plus 2 equals x plus 2. Now this is very important. When we square both sides, for the radical and the square will cancel out. On the other side, we're squaring this entire expression, x plus 2 squared. This gives us x plus 2 on the left-hand side equals x plus 2 all squared would be x squared plus 2x, which is 4x plus 4. That's FOILing out x plus 2, x plus 2 times x plus 2. What we're left with here is a quadratic equation. For quadratic equations, we want to move all of our terms to one side and then try to factor to solve. So here, if we move all of the terms to the right-hand side, we get x squared. 4x minus x leaves us with a plus 3x, and then 4 minus 2 plus 2. So this factors very nicely, actually, to x plus 2 times x plus 1 equals 0. Then if we set each factor equal to 0, x would be equal to -2 and x equals 1. Now, very important. Remember, we cannot take the square root of a negative number. So you do want to go back and check to make sure that under the radical, the expression does not simplify to a negative number when you plug these values in. -2 plus 2 would be 0. That's fine. Should be negative. -1 plus 2 is positive. So both of these solutions work. All right, on to B. The square root of x minus 5 plus 5 equals x. If we subtract 5 from both sides, that's the square root of x minus 5 equals x minus 5. And then if we square both sides, we get x minus 5 equals x minus 5 squared is x squared minus 10x plus 25. And then we move everything over to one side, factor and solve. This would be 0 equals x squared minus, is that 11x, and then plus 30. So we want factors of 30 that add to -11. That would be -5 and -6. So 0 equals x minus 5 times x minus 6. And then setting each factor to 0 gives us x equals 5 and x equals 6 as our solution. And if you plug both of them in, they will work. All right, last one of these. X plus 4, the square root of x plus 4 equals x minus 2. This one's already isolated for us, so we can go straight to the step where we square both sides. We'll get x plus 4 equals x squared minus 4x plus 4. That's what x plus or minus 2 squared is. And if you can't see why I'm getting that x minus 2 squared is this trinomial, remember it's x minus 2 times x minus 2. Then you have to FOIL. Okay, x squared minus 5x, and the 4's cancel out, so plus 0. Then we can factor out an x. That's 0 equals x times x minus 5. Sorry, I'm just making sure I believe me, you guys. You know, sometimes I don't trust myself. Okay, and then we have x equals 0 and x equals 5 as our solutions. All right, do both of these work? Now, this is the part where I don't think both of them work. For the check, when we plug in 0, that's where we get a problem. The square root of 0 plus 4 equals 0 minus 2. Is this true? This is telling us that the square root of 4 equals -2. That does not work. So 0 as a solution, when we plug it back in, it actually doesn't help us. It doesn't give us a true solution. It's an extraneous solution, so we can ignore it. When we check 5, though, things work out. The square root of 5 plus 4 equals 5 minus 2. That's the square root of 9 equals 3, which is true. For example 3 here, we're solving square root equations still, but this time we have square roots on both sides of the equation. So let's see how that works out. If you have square roots on both sides of your equation, you want to isolate one of the square roots. If one of them's isolated, like in part A, 3 minus the square root of x equals the square root of x minus 3. The right-hand side of the equation is isolated. So then we can go straight to squaring both sides. So we're going to take 3 minus root x and square it, and then square the square root term as well. And this gives us 3 squared is 9, and then minus 6 root x, and then plus x. We need to isolate our radical again. So now we started off with 2 radicals, we squared both sides. Now we have an expression that only an equation, that only contains 1 radical. So we're going to solve for the remaining radical, this one, and then square again. We can do this, team. Okay, so from here, we need to subtract x from both sides. Might be helpful if I write this out down here. We're going to subtract x from both sides and subtract 9 from both sides. That'll leave us with negative 6 root x equals negative 12. And then if we divide both sides by 6, or negative 6, the square root of x is equal to 2. And then we can square again. Squaring both sides gives us x is equal to 4. So again, what's the technique here? You want to, if you start off with radicals on both sides of your equation, isolate one of them, square both sides. You're going to end up with 1 radical still in your equation, then isolate that radical and square again. And if we check this, 3 minus the square root of 4, there's 3 minus 2, which is 1. And then the square root of 4 minus 3 is the square root of 1, which is 1. So it does check out. For cube roots, just like for square roots, we square to get rid of the square root. For cube roots, we will cube to get rid of the cube root. So isolate the cube root term and then cube both sides of the equation. All right, so for the cube root of 3x minus 2 plus 2 equals 1, first step is to subtract 2 from both sides so that we have the cube root term isolated. This would be 1 minus 2, negative 1. Now I should say this, for a square root equation, if you end up trying to isolate your square root term and you get your square root equals a negative number, remember, that's not possible. Our square roots can't be equal to a negative number. So you would just stop it for a square root equation there. For a cubed root equation, your cubed root can be equal to a negative number. So this we can continue on with. All right. From here, we will cube both sides of this equation. So the cube root and the cube cancel each other out. Negative 1 cubed is negative 1. That gives us 3x minus 2 equals negative 1. Adding 2 to both sides gives us 3x equals 1, and then dividing by 3, x equals 1/3. And that's it. I'll do one more of these and leave the other example for you to practice. Let's do the one with both cube roots on both sides. It actually simplifies very nicely. If you have cubes on both sides, we're going to, or cubed roots, I'm sorry, on both sides, we're going to cube both sides of the equation. And then that gives us 5x minus 4 equals 2x plus 5. A simple linear equation for us to solve. If we subtract the 2x from both sides, 3x minus 4 equals 5. Add 4 to both sides, 3x equals 9. And then divide by 3. X would be equal to 3. The last type of equation that I want us to practice solving is an equation where our exponent is a rational expression or a fraction. Remember, fractional exponents are just equivalent to some radical term. To get rid of the fractional exponent, you will raise both sides of the equation to some power. So if you have like the 1/2 power, you will square both sides because the 1/2 power is the same as the cube root. If you have, like we have here in part A, the 1/5 power, that's the same as the 5th root. So we'll take the 5th power of both sides. To get rid of the 1/4 power, you raise both sides to the 4th power. Okay, so for problem A, 3x plus 1 to the 1/5 power minus 1, we need to isolate the term with the 1/5 power. If you want to, you can rewrite it also. That's the 5th root of 3x plus 1 equals 2. If we subtract 1 from both sides. Then to get rid of the 5th root, or to get rid of the 1/5 power, you raise both sides of the equation to the 5th power. This will give us 3x plus 1 equals 32. Subtracting 1 gives us 3x is 31, and dividing by 3, x is 31 over 3. We'll just leave it like that. For part B, 5x minus 1 to the 1/4 power. To get rid of the 1/4 power, you're going to raise both sides to the 4th power. Remember, that's the same as the 4th root. So this would be the 4th root of 5x minus 1 equals 4 minus 2, which is 2. Raising both sides to the 4th power gives us 5x minus 1 equals 16. And then add 1, 5x is equal to 17, divide by 5. X is equal to 17 over 5. All right, team. Last type of problem that we're going to look at is an application problem where we have to use the Pythagorean theorem to help us solve. So please do recall the Pythagorean theorem. If you have a right triangle, the two sides of the triangle that form the right angle are called the legs, and the longest side of the triangle is called the hypotenuse. And the relationship between the length of those three sides is, we call the legs A and B and the hypotenuse C. A squared plus B squared equals C squared. Again, this gives us a relationship between the length of the sides of a right triangle. For a problem, or for example 6, I'm sorry, it says, for a right triangle with legs of 3 inches and 4 inches, find its hypotenuse. That's part 1. And then for part 2, a rope is needed to support a 32-foot pole. The rope needs to be attached to the pole at a distance of 19 feet from the base of the pole. How long must the rope be if it must be anchored at exactly 20 feet from the base of the pole? We have a cute little picture there for us. Let's go ahead and solve 1 and 2 first, and then I'll jump down into 3. For number 1, we don't have a picture for this, but we can draw it. We have a right triangle. And we're told that the legs, or the short sides, are 3 inches and 4 inches, and we're asked to find the hypotenuse. Remember, the relationship is a squared plus b squared equals c squared. So that would be 3 squared plus 4 squared equals c squared. 9 plus 16 equals c squared. And then 25 is equal to c squared. And you might be thinking, what on earth does this have to do with radicals? When we get to this part, you see what it has to do with radicals. In order to solve for c, we have to take the square root. So if c squared equals 25, then c is going to be equal to the square root of 25, which is 5 inches. So in this case, the hypotenuse would be 5 inches. That's for part 1. For part 2, we have this lovely little picture. We see that the pole that's given to us in this problem and the rope and the ground form a right triangle. Okay, we're given that one side is 19, or one leg is 19, the other leg is 20. And essentially we're trying to figure out what C should be, what's the hypotenuse. So it doesn't matter which of the sides you call A or B. So I'll say 19 is A and 20 is B. We use a squared plus b squared equals c squared. That will be 19 squared plus 20 squared equals c squared. 19 squared is 361. 20 squared is 400. So we'll have 761 equals c squared. And if we take the square root of both sides, c is equal to the square root of 751. That is going to be a decimal, obviously. We're not told what to round to, so we can just leave it here in radical form, 27.59. So 27.59, and that would be in feet. That's what C is approximately equal to. All right, last one of these. Ooh, an object is dropped 40 feet from a bridge above a river. Okay. Use the function T of H equals the square root of H over 4. Okay. T equals the square root of H over 4 to find the time it takes for the object to hit the water. H is the height at which you're dropping the object from. If you take the square root of that height and divide by 4, that gives you an approximation of how long it takes for the object to hit the ground or hit the water. Okay, so in this one, T would be equal to the square root of 400 divided by 4. The square root of 400 is 20, and 20 divided by 4 is 5. So this is saying that it would take approximately 5 seconds for the object to hit the ground.